In this video, we're going to talk about the first learning objective for section 3.2. We're going to use the second derivative test to classify the relative extrema of a function, okay? You do know how to do this already, really. From 3.1, we used the first derivative test. You check the sign to the right of it and to the left of that point. And if it had like a decreasing to the left and increasing to the right, then you said that was going to be a relative minimum. If you had increasing to the right and decreasing to the left, then you call that relative maximum. So you do know how to find these relative extrema already, but we're going to use a slightly different strategy called the second derivative test in this video. Now, my plan is to go over numbers, example 1, 2, 3, 4. 1, 2, 3, and 4. So I'm going to stop after finishing page 3. I will come back and go over how to, well, the second objective, we're going to graph a continuous function in a manner that shows concavity. And not only that, we're going to sketch some graphs. In example 5, we will also try a couple graphs where we have to use the graph given and find the parts. Now, the second video will help you on some of the homework problems that you will do on 3.2. But after watching this first video where I go over example 1, 2, 3, and 4, you should be able to try the 3.2 problem, okay? So 3.2 problem, I'm just going to give you one function and ask you to complete part A, B, C, and D, okay? This is due this Sunday, but please try to submit them early because I love checking your work throughout the week. Now, if you want to download this note file, I did post that on Canvas for you. Under week 10, here it is, Math 261, section 3.2 note. So if you want to print it out, go through the notes with me, that's great too. But I don't think you have too many things to write. Maybe the graphing will be helpful because you're going to have the graph to the right of it and to the left of it to look at. But the 3.2 problem, I also made a submission link. This is where you're going to submit the daily problem for this lesson. Also the homework, 3.1 homework and 3.2 homework are all available on Canvas. I was getting worried because I'm getting emails from some students about, hey, what are we doing about our class? But you know, we've been making announcements on Canvas and I thought I was teaching in the last 2 weeks. But I think some of you are not getting the notifications when I write these Canvas announcements. But I'll try to reach out to certain people who are non-responsive. But, you know, we still have our class going on, right? But one more thing before I start the lesson, though, about this one announcement that I made yesterday. You do know that all classes at Nova are now pass or fail for spring 2020, right? So what I did was I removed A, B, C, D, or F next to your numerical number the grade and just replaced it with PT, PN, and NP. What you want is PT. You want pass transfer, okay? That's going to be a grade of C or above, A, B, or C, so that you can actually transfer this credit. PN, that means you're passing, but you got a D. NP will be if you have lower than 60. But just as a reminder, this grade, this pass or fail grade, does not impact your GPA for this semester. So if you have any questions about this, you need to email me, okay? And if I don't have an answer, I will forward your question to the academic dean, and maybe we can find a solution for you. All right, here we go. Let's go ahead and start our 3.2. Going back to my note. Here we go. All right. The second derivative test is using the second derivative. So what you're going to have to find is you're going to have to find f double prime of x. Okay? So today you're going to find the second derivative. And you're going to use that to tell whether it's a relative minimum or relative maximum. But first, you will need to find the critical value. So critical value C must be found first in order for you to use this second derivative test. So let's read this. Suppose that f is differentiable for every x in an open interval and that there is a critical value C. A quick reminder, how do we find critical value C? Well, you first have to find the first derivative. And what you're going to have to do is you're going to set it equal to 0, right? Or you have to find a point where your first derivative does not exist. Now, all the examples that I got ready for you today are just polynomials, so just check the first case. Find where your first derivative is equal to 0, and that's going to be your critical value. Now, you have that critical value, and we'll call that C. Then we're going to say that this value, if you plug it into the function, will give you our relative minimum if the second derivative comes out to be positive. So what you do is you first find your critical value C, okay? And then you're going to plug in that value into your second derivative. If the value comes out to be positive, then we know that's going to be relative minimum. Well, what if it comes out to be negative? If the second derivative, if you plug it into the second derivative function and you get a number smaller than 0, then we're going to call that f of C is a relative maximum. So that is the second derivative test, and we will be using this in our examples 1, 2, 3, 1, 2, 3, and 4. So I'm going to box this. Now, you don't have to use this because you do know how to use the first derivative test from section 3.1. And you're going to have to use the first derivative test if you get a special case, like you get the second derivative to be exactly equal 0. Then you're going to have to go back and use the first derivative test to determine whether this is a relative maximum or minimum. But let's try that. Let's use this new method today, and I want you to use this new method on your classwork, okay? All right, example 1, kind of similar to what you're going to do for your classwork problem. But in example 1 and 2, I'm going to do part A and B only. Example 1 and 2, I'm going to do part A and B only. Okay, A and B. A and B. And example 3 and 4, I'm going to do the other part. It's really C and D, but, you know, they're back to A and B. But after seeing all these examples, you are going to be able to do your classwork problem, okay? All right, but you still need to come back and watch the second video because that's going to help you to sketch graphs and read graphs, and definitely on your 3.2 homework. All right, let's try number 1 together. For the following neither. Let me do that first. Okay, let me do that first. So what do we need? We need critical values. Let's find critical values first. Oh, critical values. So in order for you to find them, we find the derivative and we're going to set it equal to 0, right? So f prime of x is, let's take the derivative of this polynomial, okay? 3x squared plus 6x minus 9, right? Now let's set it equal to 0. And on the right side, I noticed that 3, 6, and 9 are all divisible by 3. Let's factor out the 3. If you factor out the 3, you'll get x squared plus 2x minus 3. Now that is also factorable. So we're going to factor that trinomial as x and x, 3 times 1. Make the 3 a positive, make the 1 a negative, and now we factored it completely. Alrighty, now we're ready to find our critical values. So this factor will give you x equals negative 3. So we have our first critical value. And the second one is x equals positive 1. Good start, good start. Now, because we want to use critical points, I want to find the x and y value both. So while I'm here, I'm just going to go ahead and find what is f of negative 3 and what is going to be f of 1 so that I can have a point instead of just x value alone. So for f of negative 3, I need to plug in negative 3 into the original function. Minus 9 times negative 3 minus 13. Alrighty, I'm going to grab a calculator. around me somewhere. Alrighty, give me 1 second, guys. I am walking around my house. Oh, there it is. There's my calculator. Okay. Alright, I am typing this in. Negative 3 cubed plus 3 times negative 3 squared minus 9 times negative 3 minus 13. I got 14. What a nice number. 14 is the y value. So, the first critical point is, well, this will give me negative 3, 14. All right, let's find the other one. Plug in 1 into the original function. And I want you to do that on your classwork to find your y values, okay? So that will be 1 plus 3 minus 9 minus 13. And that got me negative 18. 1 and negative 18. So these are my two critical values. So these are, well, I should say critical points now because I have points now. All right. Now, this is nothing new so far, right? You know how to get up to this point. But now I am about to use the second derivative test. You ready? Last class, what we did was we just drew a number line and then we checked the signs to the right and left of each of these critical values. What we're going to do is we're going to find the second derivative and use the second derivative test. Let me change the color of my pen to blue. All right, so I'm going to say find the second derivative. Okay, so what's the f double prime of x? And let me show you what I'm using, okay? I'm going to look at this right here, and then I'll just take the derivative of that, okay? So that's going to give us 3x squared will give us 6x, plus 6x will give us plus 6. 9, no more 9, right? So we found the second derivative. You don't want to take the derivative of, this mess right here. You don't have to. I just went back to the standard form and found the derivative from there. Now, what we're going to do is we're going to plug in our critical values in here. And quick reminder of what that second derivative test said. If you plug it into the second derivative and you get a positive value, then you know this is going to be relative minimum. Okay, so that's what we're going to test now. If you get a negative, then you're going to say that value is going to be relative maximum. Okay? Let's try. So plug in your critical values into this second derivative. So let's first find f double prime of negative 3. Okay? I'm going to plug in the first critical value in here. Okay? That's going to be 6 times negative 3 plus 6. That's negative 18 plus 6. That's going to be negative 12. Well, this is negative. Okay, I'm going to go ahead and talk about something that we never really saw yet. Negative second derivative means this is concave down. Concave down. And you know how I memorized it when I was in school? Negative second derivative means concave down. When I think about the word negative, I think about a frowny face, okay? So that's my little frowny face. So if the graph will look like that, I'm going to have a relative maximum. Okay? Relative maximum at negative 3, 14. Okay? And now let's just double check, okay? Negative maximum, right? If the second derivative is negative, then we have a relative maximum right there. So yes, I'm going to keep on doing my frowny face for any time I get a negative second derivative. Now let's try the other one. Let's plug in the other critical value. What was it? That was positive 1, right? What is f double prime of 1? That's going to be 6 times positive 1 plus 6. You'll get 6 plus 6, so that's 12. And 12, this 12 is positive. And when I think about positive, well, I think about a happy face like this. And just ignore the little eyes here. Just focus that this curve will have a relative minimum. And I'll write it down. This is going to be called concave up. And let me make notes here. Concave down. I think the order may be a little messed up because maybe I should have talked about those first before I do these examples. But don't worry, I'll get there. We'll get there together. So relative minimum at what point? 1, negative 18. So we just completed part A using the second derivative test. Because the second derivative came out to be negative for negative 3. When you plug in negative 3, we said negative 314 is a relative maximum. And because when we plugged in positive 1 into the second derivative, the value came out to be positive. So we said that's going to be a relative minimum. So I want you to use this strategy today on 3.2 classwork instead of the first derivative, okay? Now, what else do we have to do? We're going to have to identify intervals where the function is increasing or decreasing. Guys, I'm reading this part right here. Identify the interval where the function is increasing or decreasing. And if we got all the way here, that part is going to be easy. Now, let me go ahead and do a quick sketch of the graph. Okay? Sketch. On a number line, here's my y-axis and my x-axis. Let's say that I have 1, 2, 3, and 14. My y-axis is not drawn to scale. But here's my negative 3, 14. And what we know that is that this point is a relative max, right? We just found that. And what's the other point? 1 to the right, down 18. Just going to have a point like that right there. And this is going to be our relative minimum. So I'm going to do a quick sketch right here, okay? So I'm going to have a graph like this. This will be the relative maximum, so I should have a graph looking like that. This is the relative minimum, so I'm going to have a graph looking like that. And I'm just going to connect these two in the middle. I'm just going to extend it to the right and to the bottom. So here's my graph. Hello, here's my graph. So let's go ahead and read the intervals here, okay? Just making sure that you can read my numbers here. That's 1, negative 3. So I'm out of room, but I'll try to squeeze in my work in here, okay? So this graph is increasing on the first section, negative infinity to negative 3 and positive 1 to positive infinity, right? And this graph is decreasing on the middle section, right? You see that this graph is decreasing from negative 3 to positive 1 right there. So decreasing on negative 3 to positive 1. So I didn't do the sign. I did not use the first derivative test. But using the second derivative alone, knowing which one is relative maximum, which one is relative minimum, I was able to figure out the graph or sketch the graph and tell the increasing or decreasing interval. All right. It's really this. This is what we're going to do. Now, let's try another one, number 2. But this one I prepare so that it comes out to be, we're going to have to go back to the first derivative. Okay, but let's try number 2 together. I don't know how long I've been going, but, sometimes if my video is too long, remember last time it didn't save on my iPad, so I had to record the whole thing. So just because I'm getting super worried, I'm scared that I lost all my work. After example 2, I may stop it and then come back and do example 3 and 4, okay? Alrighty. For the following function, give coordinates of any critical points and classify each point as a relative maximum. Let's try that one again. A, I'm going to find critical values. That's where my G prime is going to be 0. So let's find G prime. G prime is going to be 20x to the third power plus 60x squared. Oh, this is your second homework problem. I just clicked on similar problems to get like a random example because I wanted to go over this one with you because you will see this on your homework. Just double checking my derivative. Yes, and yes, okay, that looks good. Okay, let's set it equal to 0 and let's factor out the GCF on the right side. I can divide both of these by 20x squared. If I divide each term by 20x squared, I will get x plus 3 inside. That means my first critical value is x equals 0. And my second critical value is x equals -3. I already know something fishy is going on. Take a look. This 0 right here, x squared. That one has even multiplicity, so we're expecting the graph to bounce. So this one, x equals 0, I'm expecting it to be neither maximum or minimum. But we'll see. Now, let's go ahead and, well, I do want to find the y values. So let's find y values. Find g of 0. Which is going to be, well, let me write these down first. G of -3, because we want to talk about critical points, not just critical values. I want to find the y values too. So 5 times 0 to the 4th power plus 20 times 0 to the 3rd power. Oh, that's just going to be 0. So the first critical point is 0, 0. The second critical point will be 5 times -3 to the 4th plus 20 times -3 to the 3rd power. And I may want to get a calculator for this. All right, 1 second. I'm typing this in. 5 times -3 to the 4th plus 20 times -3 to the 3rd power. That came out to be -135. So let me write down the second critical point is -3, -135. Alrighty. Okay, so I got my critical points. I am about to find the second derivative so that we can use the second derivative test. So find G double prime. Okay, so G double prime of x, the second derivative is equal to, I'm going to use this right here, okay? 20x cubed will give us 60x squared plus, now what about this term? That will turn into 120x, right? So we got the second derivative. What we're going to do now is set this equal to 0. No. I'm sorry. Not set this equal to 0. I am using the second derivative. So what do? We plug in our critical values in here. Okay? So let's find that. G double prime of 0. That's going to be 60 times 0 squared plus 120 times 0. Uh-oh. What's that going to give us, guys? That's going to give you 0. So, the second derivative test failed on us. You know why? Because look. If the second derivative comes out to be 0, this is the third case. They told us to, hey, go back to the first derivative test. So, unfortunately, this is the case where we have to actually go back to what we learned in lesson 3.1. So great way to review, right? Let's review then. So reviewing, gotta use the first derivative test now. So let's try that. I'm going to do it on the side over here. So put the 0 right in the middle. We're going to find, now notice the first derivative test, you must use the first derivative, right? Not f prime, but I should say g prime. G prime was to do 20x cubed plus 60x squared So I'm going to plug in a positive value into G prime. If I plug in 1 in there, what will that be? That will be 20 times 1 cubed, oopsie, plus 60 times 1 squared. And we know that's going to be positive, right? That's going to be positive, which means our function G is increasing. That's the first derivative test. Well, not complete yet. Increasing. So going up there. Now let's plug in a value that is to the left of this. Let's find G prime of -1. That will be 20 times -1 cubed plus 60 times -1 squared. Okay? So what's that going to be? Let me actually get a calculator and find the value. 20 times -1 cubed plus 60 times -1 squared. That's going to be positive 40. This is another positive. Okay? This is positive again. That means, well, same conclusion. G is increasing here. So this graph right here is increasing to the left of 0, increasing to the right of 0. That's why, you know, we're not, well, what are we going to call? 0, 0 is a critical point, but it is neither a relative minimum or maximum. Okay, so that's the conclusion for our special point 0, 0. It was simply just going up and then kind of stopped going up for a second right there and it started going back up there. So and that can happen, right? That can happen. But that wasn't the only critical value that we had. So let's plug in the other one, right? The other critical value was -3. So let's move on and do that one. What is G? Now remember, we're back to our second derivative test. We're done with our first critical value. We're done with him. What's G double prime of? -3. Let's plug in 60 times -3 squared plus 120 times -3. I hope this doesn't come out to be 0. 60 times -3 squared plus 120 times -3 is 180. Yay! This came out to be a positive number. If it's positive, you know what I draw? I draw a happy little face, whose little mouth is making a concave up case. That means we have a relative minimum. Of course, I have to come back and talk more about this concavity and why, you know, what does that even mean? But I'm going to do that in my, probably now going to be a third video where I use the graph and, you know, and going to give you a definition of concave up, concave down, all that. But for right now, I mean, we are strictly just using the second derivative test. If the second derivative comes out to be a positive value, we know that it has relative minimum at that point. So relative minimum is at -3, -135. Okay? In order for us to tell where this is increasing or decreasing, we will need to sketch this real quick. Okay? Alrighty, let me sketch this over here in my tiny little room. Where's my first one was 0, 0, right? Now this, we already know what it looked like. This one was increasing to the left, kind of stopped a little bit, and it's increasing again. But let me plot my -3. Hold on a second. I should probably erase this because my other one was at -3, and I'll just say that is -135. -3, -135. So using the fact that this was relative minimum, I'm going to have a graph that looks like this right here. Okay? So it's going to go up. It's going to go up and touch that point to the right. But this is going to keep on going up because we did say increasing and increasing to the left and right of that 0, right? So it's going to keep on going up, something like that. And this is just going to go up right there too. So this is the graph, a sketch of it. But with you having a graphing calculator, if the sketching part is a little bit challenging, you can use your graphing calculator to look at it if you want to. But let me go ahead and write these intervals down, okay? So we're going to have decreasing on -infinity to -3 and increasing on -3 to +infinity. I would, you know what, guys? I will separate this interval into -3 to 0 and 0 to +infinity. And I was doing your homework, you know, before I assign it to you. I always try to do it. And when I typed it in as two separate interval notation, they didn't like it. So if it does that when you're doing your homework, just type it as a single interval. I don't agree with it, but well, like this. The entire thing was increasing from -3 to +infinity. So that's probably a good stopping point for the first video. We talked about using the second derivative test to find whether it's a relative minimum or maximum. But if that second derivative fails on us, then you have to go back and try what you learned in 3.1, the first derivative test. So that's example 1 and 2, just example 1 and 2. But this is taking a little bit longer, so we're going to come back and talk about a test for concavity and how to find point of inflection in our second video, okay? All right, please